Math isn't difficult. Math is fun. I am Neelakanta Bhanu Prakash and I am the fastest human calculator in the world. And we are exploring infinities. Exploring infinities is here in front of you to give you a mathematics learning experience like never before. With expert trainers from around the country, we are here to make you learn math the right way.
Hello, welcome back. I'm Anshika from Exploring Infinities, and this is the second lecture for the chapter Linear Equation in Two Variable. So let's do a quick recap of whatever we have done till now. So we have not done much. So it's just the introduction we did to our chapter Linear Equation in Two Variable. So we did. I did introduce to you the story of Tom and Dana. We got two linear equations from there. We concluded that if we needed a unique solution for a linear equation in two variable, we need minimum two linear equations in two variables for that particular unique solution. So then I told you what exactly is a solution. So we saw that if we have a linear equation in two variables, just one, and if we plot that on our graph, whatever points lie on that particular line when we plot them, all of them are a solution to that particular linear equation in two variable. But then we saw that when we were solving Tom and Dana's equation, we saw that Tom made a guess of 10 and 25 for the cost of bat and ball, but that wasn't satisfying Dana's equation. So it means that not every point on our line is a unique solution when it comes to a pair of linear equations. So we'll see how exactly are we going to use graphs in this class. Graphs to get a solution to a pair of linear equation. So first of all, we think that if we have two lines. Okay, two lines if you have, what all can you do with those two lines? You can either make them intersect, you can either make them go parallel to each other, or else you can make them coincide with each other. That is, both of them are the same, parallel, or else they're intersecting. So let's write down. So it means that whenever you have two lines, they'll either intersect, such that in this case they're intersecting, or else they'll be parallel to each other. So it will be like this, or else they'll coincide with each other. So this is the basic thing we know about two lines. Okay, so both are the same. That's a third possibility. So if we have pair of linear equations and if we plot them on a same graph, it means that we'll have one of these situations. So let's go one by one. So let's take our case number one to be our example of Tom and Dana's. That is the linear equations for Tom and Dana, which were 3x plus 2y is equal to 80 and 4x plus 3y is equal to 110. These were a pair of linear equations for Tom and Dana. So let's see when we plot them on our graph, what do we get? So the first step to plot a particular pair of linear equation or any linear equation for that matter is that we make this table. So I'm taking y to be equal to 80 minus 3x upon 3x upon 2. So this is my y. This is what I'm taking my y to be. So now what I'll do is what we do usually to plot a graph. We just keep on putting some random values to the x, and then we find the answer for y. So I give my x to be 0. So I'll get 80 minus 3 times 0 by 2. So the answer is 40. So I have my first point as 0, 40. Now second point, this is Tom's equation. So Tom made a guess of x is equal to 10, right? So for that he got 25. And now we'll probably plot one more point. We'll probably take our x to be 20. So I get my y to be 10. So this is the first box I'm getting. So using this, I plot my line for Tom's equation. So similarly, on a similar fashion, I get the points for Dana's equation. So it will be y is equal to 110 minus 4x upon 3. So when I plot this, I get, if I put my x to be 0, I get 36.6 somewhat. If I again give the value probably 20 over here, I'll get 10 here. And then if I give minus 10, I get 50 over here. So I'm getting these particular points for my Dana's equation. Now if you take a look on these two tables, you can see that there's this one common point that we can locate, that is 20 comma 10 and 20 comma 10. And if you remember in the last class we saw that the one extra bat's cost was 20 rupees and the one ball costed 10 rupees. So it means that 20 comma 10 was actually our solution when we solved a pair of linear equation using the model method. So here again we saw that when we tried plotting these two graphs by using these points, these tables, we saw that we have a common point over here. So it means that this particular common point that we get is the solution to our pair of linear equation. So if you try plotting your graphs for these two particular pair of linear equation, you'll get somewhat like this. So this is my pair of linear equation, 3x plus 2y is equal to 80 and 4x plus 3y is equal to 110. So I plotted them on my graph and I got this as their answer, that is their common point of intersection. It means that a solution for a pair of linear equations using graphical method is where both my lines are actually intersecting with each other. So my common point of intersection for both the pair of linear equation is my solution to the pair of linear equations. Like for in this case, I'm getting 20 comma 10 as a common point of intersection for this pair of linear equation, and that becomes a solution for a pair of linear equations. Okay, so what we say is these are a consistent pair of linear equations. So whenever you have this one point of intersection for both your lines, you say that they are consistent pair of linear equations. Consistent pair of linear equation, and this always gives you a unique solution. Okay, so this is our first case using the Tom and Dana's example, where we saw that we have consistent pair of linear equations which gives me a unique solution, that is common point of intersection using my graph, that is 20 comma 10. So let's see another example, our next example. So again I'm taking two random random linear equations. So my example is x plus 2y is equal to 4 and 2x plus 4y is equal to 12. So now again what the first step we do to get our answer is plot them. So for plotting them, I again make my table. So x and my y will be equal to 4 minus x by 2. So again I give the values, I get 0 comma 2 and then 4 comma 0. So I again get my table for this particular equation. Similarly, if I try putting up a table for this particular equation, I get 0, 3, 6 and then 0. So this is the table that I get for my pair of linear equations. So now if you try plotting them on your graph, so if you try plotting them on your graph, you get somewhat like this. So as you can see, the red line represents x plus 2y is equal to 4 and the blue one is 2x minus 4y is equal to 12. So you can see it's not intersecting anywhere. Like anywhere till you can actually move your graph. It's not intersecting each other anywhere. So this is the second case I talked about, the parallel lines. That is, they both are parallel to each other. The graphs of these two lines are parallel to each other. So we say that these are inconsistent pair of linear equations. And they have no solution. As you can see, there was no common point of intersection, so it means there was no solution. And also you can see, just by looking at these two tables, there was no common point where they were actually coinciding with each other. So that means whenever there is a common point of intersection which becomes a solution, which is not there in this case, we have a parallel line in this case, so this gives a no solution to us. So let's see my case 3. So I'm now giving a different linear equation. So this time my linear equation is 2x plus 3y is equal to 9 and 4x plus 6y is equal to 18. Again, what we do normally, we plot our graph. So I have x and y. So if I put my x0, I get y3, and if I put my y0, I get x 4.5. So I have table for my first equation. My second equation is, if I put x0, I get y3. If I put y as probably 1, so I get my x to be 3. So I again get my pair of table for my linear equation. So now again I want you to plot these two graphs in your graph papers. So when you plot them, you'll get somewhat like this. Actually, they both are lying over each other. When I select my red color, that is 2x plus 3y is equal to 9, I have this graph. And if I go to my second equation, that is 4x plus 6y is equal to 18, it's right above my red graph. So it means that this lies in the third case that I was talking about, that is, they're coinciding with each other. So it means that every point on that graph is a solution. So it means they are dependent pair of linear equation, and it has infinitely many solutions. That is because every point of both the both the lines are coinciding with each other. So every point is a common point of intersection, which makes our situation for a dependent pair of linear equation, that is, they are coinciding over each other and they have infinitely many solutions. So these were the three cases where actually your pair of linear equations can actually lie. So it means whenever you have a consistent pair of linear equation, you'll get a unique solution to it, and you will have common point of intersection when you plot them. So second is, when you plot two pair of linear equation, you have parallel lines. It means they are inconsistent and they don't have any solution because there is no common point, because they are not intersecting with each other at all. The third case is when they both are lying over each other, they're coinciding with each other, they become dependent pair of linear equations and they have infinitely many solutions. So these are the three pair of linear equations that we analyzed today, and we realized that the first one was intersecting with each other. So it had a common point of intersection, therefore it has a unique solution and was consistent. So let's keep on writing what we actually have with us. So we have these as intersecting pair of lines, and we saw that we called them consistent pair. Okay, so we have a unique solution for this pair. Okay, so the second pair we studied, it was parallel to each other. Those two lines were parallel to each other. So they were parallel lines, and we called them inconsistent pair of linear equations, and we saw that it has no solution because they were not exactly intersecting with each other at all. The third one we saw that it was coinciding with each other, so we have coincident lines. We saw that we call them dependent pair of linear equation, and then we saw that it has infinitely many solutions. Okay, so we have this much with us. So let's summarize, let's see what is exactly the relationship that we'll probably get. Probably we can generalize something from here. So what we do is we check the relationship between their coefficients, that is a1, a2, b1, b2, c1, c2 and all. So we see what is exactly the relationship between them, and then we see if we get any conclusion from there. Probably just by looking at the equation you can say that if they're consistent or inconsistent or probably dependent. Let's see if we get any conclusion from there. So a1 by a2 in our case, this is 3 by 4. Okay, so I'm just writing down a1 by a2, b1 by b2 and c1 by c2 and seeing if we get any result. So b1 by b2 in our case is, this case is 2 by 3. Then we have c1 by c2 as 80 by 110. So from here, what exactly, no, let's just write down a1, a2, b1, b2 for all of them. So here again a1 by a2 is 1 by 2, then I have 2 by 4, then I have 4 by 12. If I try reducing them, I have 1 by 2 and 1 by 3 over here. Okay, so now in this case I have 2 by 4 which is 1 by 2. I have 3 by 6 which is 1 by 2. I have 9 by 18 which is again 1 by 2. So in this case, as you see that in the third case, my a1 upon a2 was equal to b1 upon b2 equal to c1 upon c2. So in this case I got a conclusion that my a1 upon a2, b1 upon b2 and c1 upon c2, the ratios were equal to each other. In this case, the second case, my a1 upon a2 was equal to b1 upon b2, but it was not equal to c1 upon c2. Okay, so I got a conclusion here also. But in the first case, I saw that none of the ratios were equal to each other. So I just simply write a1 not equal to a1 upon a2 not equal to b1 upon b2. So here I have a relationship between the coefficients of my linear equations, a pair of linear equations, that if my a1 upon a2 is not equal to b1 upon b2, then definitely I have a consistent pair of linear equation which will give me a unique solution. So if my a1 upon a2 is equal to b1 upon b2, then it will be either equal to c1 upon c2 or else it won't be equal to c1 upon c2. And if it is not equal to c1 upon c2, I can say that it is an inconsistent pair of linear equation with no solution. And if it is equal to c1 upon c2, I say that they are dependent pair of linear equations with infinitely many solutions. So this was our whole task, to exactly see through the graphical representation of my pair of linear equations, then what is exactly the relationship between the coefficients of my pair of linear equation, using which I can say simply by just looking at the equation if they have a unique solution or if no solution or if they have infinitely many.
And so we come to an end to today's lecture. Thanks a lot for watching this, and stay tuned for the upcoming ones. Don't forget to follow @FastestHumanCalculator and @exp.infi on Instagram, and subscribe to our YouTube channel.